Welcome engineering static students. This is ENGR ampersand 214 being taught at Bellingham Technical College. The topic of this lecture is a review of the vector dot product. The most important thing we will do with the dot product is to find portions of vectors that are parallel to or in a given direction of interest that we have. So we will use the practical definition of it to get what we want in a statics analysis problem. But we will use the specific algebraic definition of the dot product to give us an easy way of getting at it without having to necessarily go through the geometric relationships. So for those of you who have taken any kind of vector algebra in your mathematics, this will be a review. If you haven't, don't worry. I'm going to step through the definitions, both the algebraic and then the practical applications, and then you'll have a whole bunch of places to use it in your statics homework. Okay. We have two definitions that we can use for the dot product, and just to back up a bit, vector multiplication. If you listen to some of the previous lectures, one or the other, you got some exposure on adding and subtracting vectors. So commutative property of addition, how to make an additive inverse by basically reversing a vector's direction on itself and going back collinear the same magnitude. You dealt with distributing a scalar over a vector and then applied it to use vector magnitude and find magnitude of a vector in a couple of different directions. What you didn't see was actually multiplying a vector by another vector. Well, as it turns out, there's two different ways to multiply vectors. One that basically can be defined as the scalar product, and that's the one that we're going to deal with today, the dot product. And the other is called the cross product or the vector product because it gives you a vector. They're both similar in that they are really portions of a matrix operation that you can perform on two vectors. We will not get into that part of the definition, but we'll use parts of it to create the definition. So the definitions we'll use. So we're going to start with the two different things that we'll use from the vector dot product. We're going to start with the practical one. First is how we note it. If I'm going to say I want the vector dot product of vector f and q, I literally write a dot. So it's sort of like a multiplication with an asterisk on your keyboard. So I would read this as f dot q. Okay, what does that equal? Well, it equals a scalar. Notice everything over here isn't a vector anymore. I end up with the magnitude of vector f, which is a scalar, the magnitude of vector q, which is a scalar, and times the cosine of the angle between vectors f and q. So if you think about what the definition of cosine is, another way that this can be interpreted is the portion of f that is in the direction of q, or the portion of q that is in the direction of f. So the portions of each of these vectors that are parallel to each other. That's how you interpret the cosine theta of the angle between the two. And that's something you can actually work out with a geometric figure. If we want to describe this algebraically, there's actually an algebraic definition of the dot product. So we gotta write our vectors in orthogonal directions to do that. And so I've got f and q written out with their component parts. This is f sub x in the I hat direction, plus f sub y in the j hat direction, plus f sub z in the k hat direction. So it's kind of like x, y, z directions. And the same with q. Okay, so we snuck in another property here, which we'll skip for the moment. But let's just work on writing the dot product. Okay. So the way we're going to do this is to actually use good old FOIL method. So we're going to pretend we're back in elementary algebra class, and we're going to use that first, outer, inner, last. And so we're actually going to multiply these two vectors out, and we're going to use what we know about the properties of unit vectors, given this definition up here, to multiply the unit vectors by each other using this relationship. and using what we know about the angles between I, J, and K. And remember, they're the coordinate axes, so they are at 90 degrees to one another. So we're going to start our multiplication here. So I'm going to go first. So I'm going to multiply f sub x I hat times q sub x I hat. So that will give me this term down here. So I have, notice I don't have the arrow and I don't have the lines, but without an arrow, this is the magnitude of the portion of f that's in the x direction, likewise q sub x. So I have the magnitude of f sub x times the magnitude of q sub x, a couple of scalars, times I hat dot I hat. That's an I hat there. Okay, what's I hat dot I hat? That's a unit vector in the x direction times dotted into a unit vector in the x direction. Well, what if we used our straight up geometric definition to evaluate I hat dot I hat? Well, I'd start by saying, okay, I'm going to have the magnitudes of I hat times magnitude of I hat. Well, they're both 1. So I have 1 times 1. Okay, that part's done. And then I'm going to multiply by the cosine of the angle between. Well, they're both pointed in the x direction, so they're parallel. So the angle between them is 0. What's cosine of 0? 1. Wow, well that's pretty easy. So I hat dot I hat is just 1. So I'm left with just the magnitude of f in the x direction times the magnitude of q in the x direction. Okay, so let's do my next part of the multiplication. So I multiplied first. I'm gonna get one of the inners. So I'm gonna do f sub x in the I hat direction times q sub y in the j hat direction. Okay, it's just foiling, just basically doing my little algebraic multiplication. So I get the magnitudes of the two terms. So I have f sub x, and this time it's times q sub y. So the portion of the q vector in the y direction, just the magnitude. And now I have I hat dot j hat. Okay, different direction. All right, well, I can probably use the same relationship to evaluate these two unit vectors. So I would have the magnitude of I hat, which is 1, times the magnitude of j hat, which is 1. So I have 1 times 1. It's pretty easy. Then I'm going to have cosine of the angle between I hat and j hat. Well, I hat's pointing straight exactly in the x-axis direction, and j hat is pointing in the y-axis direction by definition. They are by definition 90 degrees apart. What's cosine of 90? 0. So I hat dot j hat is 0. Now we can kind of save ourselves some work here by extrapolating this cosine theta direction portion of this vector, or this scalar product, dot product, by saying, okay, anytime we have a unit vector times another unit vector dotted into another unit vector, we've got an angle between the two of 90 degrees, and we're taking the cosine of it because we're taking the dot product. So anytime I see two unit vectors in one of these multiplication terms that are not the same, I know I'm going to have a 0 dot product because they're by definition at 90 degrees, and there's a cosine theta by definition in the dot product. So what I'm left with is just the magnitudes of the like terms. So I keep my f sub x times q sub x, and then I've got a 1 term. This goes away, this goes away, this goes away. Then I have my f sub y times q sub y times 1. This term goes away, this term goes away, this term goes away. They're all 0 because I have a cosine of 90 degrees. Then I have f sub z times q sub z times 1. So I end up with just the like terms summing up. So that's basically a shorthand way, and this is a little guide here. All of these other dots are 0, but only the like ones are 1. So you retain the like terms being multiplied and add them up. So that's the definition of the dot product, also known as the scalar product. And it's distributive. So if I have two vectors and I'm going to add them, get another vector, and then I'm going to dot that sum into another one, I can do that. Or I can distribute this C over the A and the B, and I can dot C into A. I can take the scalar product of C and A times A, which is going to give me a scalar, and then just add it to the product of C dot B. So I can do it in either order. So the scalar product or dot product is distributive over vector addition. Real handy if it's much easier to do one operation in one order. So we have that at our hands to quick draw. Okay, so we can do this with some numbers if we want. Here's a couple of vectors in 3D. So vector F1 is probably a force vector. It's pointing, we don't have units on these, could be newtons, pounds, tons, anything, tons force. So we have 2i hat plus 3j hat minus 4k hat, one vector, and the other is 1i hat minus 2j hat plus 5k hat. And somebody wants to know what is the component of their sum that's in the direction of this line. Wow. Oh man. If I had to do that geometrically, I'd be lost. I'd probably break my neck trying to find some angle between those things. But algebraically, it's a breeze, okay? So the first thing I'd want to do is find the sum, because they don't really care about, whoever asked this question didn't care about either individual force vector. They wanted to know what was going on with the sum, probably because they're looking at the sum of the forces, trying to figure out if something's in equilibrium. Maybe looking at the moment around an axis or something. So we would sum these two by adding I components to I components. Then we'd have to get a direction for this line. And to do that, we're just going to basically create a vector that goes from B to A or from A to B. Then we're going to take away its length because we don't really need it. And then we'll use the definition of the dot product to get the magnitude of whatever portion of this sum is parallel to this line. Wait a minute, what do you mean parallel? If two things are parallel, they have an angle between them of 0, kind of like I hat and I hat. They're parallel, the same thing. Two things that are parallel, also, they could be two different vectors, but if they're parallel, the angle between them is 0. And the cosine is 1. So by definition, if I take the dot product of two things and then I divide out their magnitudes, I get the cosine between. So the dot product is literally the portion of both of them that is parallel to each other. So we'll walk through that. So in this case, I started with making a vector from these 2 points. So I don't know where these are, but basically if I go from one point to the other, I can create a vector that represents that given direction. So it looks like I'm going from A to B. So the vector that represents going from A to B would just be point B minus point A. So in this case, this is a true length vector that I'm going to create. So I'm going to create some length vector Q that represents the direction of the line that's through these 2 points. So I subtract point A from point B. So I subtract each of the components. So the x coordinate minus this x coordinate gives me a -4 in the I hat direction. The 6 y coordinate minus 0 y coordinate gives me 6 in the j hat direction, and my 5 z coordinate minus 2 z coordinate gives me 3 in the k hat or z direction. So here's a vector that's parallel to the line that goes through these 2 points. Just by subtracting the 2 coordinates and using that to create a vector, I know that this vector is basically parallel to these two, to the line that goes through these 2 points. Excuse me, tongue-tied. Now I'm going to get its length. That's magnitude. So I just take my three-way Pythagorean. I square 4, get 16, square 6 and get 36, square 3 and get 9, take the square root, so that's square root of 64. And I divide each of these terms by the square root of 64, and that gives me what I call q hat, and that's a unit vector that's in the direction of this line that somebody was interested in. So q hat, which is 1 over square root of 61 times the vector that I made by subtracting the points. This is effectively my line. So this is a direction that says this is the direction that line's pointing in. There it is. Okay, and somebody wanted not one or the other vector but the sum, f1 plus f2, so that's pretty easy to get. I just add like components. So f1 plus f2 is 2i hat plus 1i hat is 3i hat. 3j hat minus 2j hat is 1j hat. Minus 4k hat plus 5k hat should give me 1k hat. Okay, so I'm going to call that f3, the sum. So I want to know what portion of f3 is pointing in the direction of q hat. Okay, so I'm going to use the definition of the dot product for that. So let's go back and see how that'll work out. So this time I have an f3 dotted into a q hat. So if I just work that algebraic dot product, it'll by definition be equal to this, which is the whole magnitude of f times the magnitude of q, which is 1, times the cosine of the angle between, which will be by definition the portion parallel. So by the definition of the dot product, all I have to do is dot f3 into q hat, and I'll get a scalar which is automatically equal to the portion of f that's going in the q hat direction. Now remember, this is important, the q hat direction. I had to get rid of the length of q first. I had to turn it into a pure direction so that when I dotted f3 into it, I was only getting the portion of f3. Otherwise I would have had some kind of length coming in from q hat. One way to do that is to keep your units with you. Q hat's going to be dimensionless. F3 is going to carry its own units, like probably force units. Let's assume it's maybe newtons. So you should get newtons in your final answer. So I assumed it was newtons here when I worked through the problem. So here's a little graphic of that. Say this point was A and this point was B. So here's my full vector q, which was b minus a. Q hat is a unit that points in this direction. And here's theta, here's my f3 going some other way, and this is the angle between q hat and f3. This horizontal vector that ends here is the portion of f3 that is parallel to q. So if I took the magnitude of f3 times cosine theta, I would get the portion of f3 that's in the direction of q. By definition, it's right there in the geometry, and that happens to be the dot product if I take the length out of q, and I don't have that in there too. So this is just the result of that. So I did f3 dot q hat algebraically, so I multiplied 3 by negative 4 divided by square root of 61, and then I added that to 1 times 6 divided by square root of 61, and then I did 1 times 3 divided by square root of 61, and I ended up with this. One of these might have been a little bit different. So distribute that back over my original f3, and this is the actual vector expression for the portion that's parallel. So that is it, and you would, by the way, get the same thing if we used going b to a for our unit vector. The cosine actually takes care of that because it would give a negative sign for the opposite direction, the way it goes around the unit circle. Okay, so that is an example of finding the portion of something parallel to something else by using the dot product. So this was 3D. This would have been very hard to do geometrically, just drawing it out and using geometry to try to find angles between and do the trig. So we'll walk through one more example here, and this one has units, so it's a little more relevant to the problems you'll be doing. So we've got a force vector with a magnitude of 8 newtons, and we have a line of action that goes through 2 points in the direction of A to B. Okay, so if we want to turn that line of action into a direction, this time we're gonna say B minus A rather than A minus B to get the correct direction. So somebody wants to know the component of that force along the line joining 2 other points. Okay, and then they give us the points. So points A and B, we're going to use that to get the direction of F. And then we're going to use C and D to get the direction of interest that we're going to try to find what portion of X is parallel to. So this lets us gives us a chance to calculate vector magnitude. We're going to need to get a unit vector that expresses the direction from A to B, and then we're going to direct 8 newtons down it, and then we're going to make a unit vector that shows the direction of a line between points C and D, and then we're going to dot them together. So again, we're using the definition of dot product to make a 3D problem much easier. So step 1, create a unit vector f hat representing the direction that the full vector f is in. Okay, so we're going to start by using points A and B. We're going to subtract A from B. So from minus, or to minus from, to get the proper vector direction. So, and then we're going to divide out the length. So B minus A, full vector is -4, 0 minus 6 is -6, 2 minus 5 is -3. We're going to divide by its full length, which is 16 plus 36 plus 9 square root. This looks like the same thing, and this time I went ahead and used my calculator and multiplied it out. So this is F hat. This is the direction along which we're going to send 8 newtons of force. Okay? So which portion of this is parallel to whatever direction C to D is? Well, let's create a unit vector that represents the direction between C and D. I'll make it easy again. So we'll write a line for CD, and then we'll divide out its length. Okay, so in this case, it doesn't matter whether we're doing C minus D or D minus C, because we're just going to make a line. It did matter when we were defining our vector, unit vector f hat, because we were specifically told it goes in the direction of A to B. But for this one, it doesn't matter. So we start by making a line. So we'll just, what did I do there? I wrote it as D minus C. So 4 minus 0 in the I hat, 1 minus 3 or -2 in the J hat, 2 minus a -4 would be 6 in the K hat. And that's what we have here. Okay, so we'll divide out its length, which is 16 plus 4 plus 36 square root. And I just wrote it as a product. So this is my direction of interest. And notice, with that square root of 56 dividing each of these terms, they're all going to be quite a bit less than 1. But if I squared them all and added them, it'd give me 1 by definition, because it's a unit vector now. So this is a pure direction. So how much of this times 8 newtons is in this direction? I'm going to use dot product and find out. So, oh, I did multiply it out. So here's my unit vector, CD. So if I squared that and that and that, added them, took the square root, I'd get 1. Always check that. It's a good check to make sure your intermediate solutions are right. So if I did F hat dot CD hat, that would give me the magnitude of the portion of F hat that's in the CD direction. So F hat's only 1 and CD is only 1, but the portion of this is in the other's direction is going to be less than 1. So I use the algebraic definition of the dot product here. So I just multiply the x magnitude times x magnitude, y magnitude times y magnitude, z magnitude times z magnitude, add them all up, keeping track of signs, and I get negative 0.37626. So it just means it's pointing backwards from whatever direction I had assumed. Okay? If I want to basically turn this into a vector symbol, this is a magnitude. If I want to distribute this back over my CD vector, saying, okay, I'm going to turn it back into another vector, which is now not a unit vector, it's less. I just redot it into CD. And so here's the portion of my 8 newtons, which direction it's going. So I multiply this by 8 newtons. It's 8 newtons times the portion of f hat that's in the CD direction times unit vector CD times 8 newtons. Gives me what I need. Now, this seems like an awful lot of kind of maybe esoteric vector algebra, and you're going, where would I ever use this? Anywhere where you have a big point cloud of coordinate locations. So if you take a part that you've just manufactured and you do a coordinate measurement analysis and you convert that into a virtual part that's basically composed of collections of points, or if you have a point cloud from a survey, whether it's a survey you took with a total station or a GPS survey, quite often we work with big clouds of points. And so with vector algebra we can relate forces and directions directly using those point pairs. So this is actually more applicable than it was perhaps in days past when we didn't work with big point clouds. So now you can actually do these vector manipulations with matrix types of programming directly onto data that you might get from a real part or a survey. Okay, there's a final example that you can work through on your own where I've just set it up and started it out, but these are all similar. Basically create unit vectors to get directions of interest, use the definition of dot product to find the portion of one vector that's parallel to another, and then use whatever the magnitudes, original magnitudes were that you needed so that you can send the amount of force or moment or whatever in the new direction you care about. Okay, and that is it for this lecture.